Hi, so at Zimmer & Peacock, we're really interested in electrochemical biosensors and electrochemical sensors, and we're very interested in the application of AI to the interpretation of signal and basically making these sensors sort of better. So in this video, I'm just going to do a quick discussion about an AI model called the LeNet-5 model. So just for your kind of interest, this model was originally, or was one of the first applications for it, was actually for reading checks. So it's pretty good at looking at an image and analyzing the image and kind of understanding the content of that image and classifying that image. Now at Zimmer & Peacock, we're really into electrochemistry, so we understand that, at first glance, the kind of things like cyclovoltammetry that we're really interested in don't look like your standard images, like a check. But in fact, I have two cyclovoltammograms running here for two different compounds, and in fact, they're quite fingerprint-like, let's say, or very indicative of the model, of the compounds behind them. So you can see that one of these CVs is kind of has a peak, and then when it comes back, we have the peak in the opposite direction. And then one of the other ones, we have a peak in one direction, and then we have you can just see it now, a peak, and then on the way back, when it turns the corner, you'll see that it gets a new peak. So these are quite distinctive. And so we think at ZP that AI, including the LeNet-5 model, is a really good way of identifying and classifying electrochemical data. So let's go on with that. So I said that we are very interested in electrochemistry at Zimmer & Peacock. Now I am going to use images actually, because we've got a side project on at the moment, and the images are of a little parasite called Trypanosoma evansi. So we have a really good collaboration going on at ZP. We have something called the developers zone, and we have members, and this is data from one of our members who happens to be interested in this particular parasite. So what we're doing, we've done other talks on AI and our increasing interest in AI, and in that we've talked about, it could be cyclovoltammetry, it could be amperometry, it could be images like this, and we've talked about you can identify features in this kind of data, and if you can identify features, we can label those features, and then we can start training AI algorithms to actually identify objects, let's say, and we can train the data. We can train these algorithms to classify these images. So this is, there's never anything new under the sun. So here we're talking about these two images. One of them represents the sort of original biological idea about neocognition. In neocognition, if you see the letter A, you see it and you understand that it's the letter A. Now, it's not, the brain actually undergoes, quite a few processes in order to, from the photons that reach the eye to the understanding that that's the letter A. These are, there's quite a few processes that go on there. So what the guys who invented this convolution neural network, this CNN, what they've done is they've basically taken the sort of processes that the brain uses, and they've translated them into processes that a computer can use. So effectively, there's sort of several processes that, the image of the cat is processed and then understood and quantified, and the output is it's a cat. But really, this is all biologically inspired. So we're going to talk about the model, we'll talk about the experimental design, and we're going to talk about results today. So first of all, the model. So the model that we're talking about here is we've taken this Trypanosoma evansi images, and we've undergone several processes of convolution, and then pooling, and then convolution, and then pooling, and then we've got a neural network, and we've classified it. So this is the LeNet structure. And I've actually, there are a lot of mathematical processes in there, and with each, we'll do different videos or different webinars about each of these processes. But there is a process called convolution, which is the first process. Then we pool it. It's easier to understand because that's averaging, and they do that twice. They convolute, they pool, they convolute, they pool. And then actually they have a neural network where all the neurons are connected, and that helps us to classify. So there's a lot of maths going on. It all happens in parallel and pretty fast. What I'm talking about sounds pretty, it can sound, you know, very abstract and not at all useful, but it's probably worth knowing that, I mean, companies like Amazon and Google and Apple, you know, they all have big AI efforts, and they're using exactly things like the LeNet-5 model. So what we've done is we've taken the images from one of our collaborators, we've put it through the LeNet-5, and we've built a model for it. So again, here's an image, and I suppose I didn't explain it earlier on, but it's actually red blood cells, and within that red blood cells there's a little parasite, and that's the Trypanosoma evansii parasite. So it's really good because our collaborator has given us something like 358 samples, 224 with the parasite, 134 without, and we created a training set, a validation set, and a testing set. And if there's a parasite in there, we call it 0, and if it's not got a parasite, it's normal, we call it 1. And then what we've done is we've cycled it, and we've taken it through several epochs. So you can see that actually our training set becomes more and more accurate, and about the 5th epoch, we've sort of approximately reached just below 100% efficiency. And our validation, if we do 7.5 epochs, then we reach about 80% validation. I'm sorry, 80% accuracy. Now this is quite nice because here we're actually testing it, and so what's happening is it's labeled that this is normal. So you look at it and you ask yourself, can you see the parasite? And so the ground truth is, or the truth of it is 1, that it's normal. And actually we predicted that it was normal. So that's a good, you know, there we're accurate here. The next image, there is no parasite. So the truth is there is no parasite, and the nice thing is we predicted that. So in fact there's good correlation all the way along, apart from 1 over here, which is about the 1, 2, 3, 4, the 5th from the end. So 1, 2, 3, 4, 5. So it has miscalled this one, and it says this is actually, the truth is there is no Trypanosoma evansii in here, and the model has actually said that there is, and so that's an error. But actually it's not a disaster because the accuracy is actually, it's 1 in 20 we made a mistake on, and the accuracy was 95%. And we've done several rounds of testing. So we got accuracies of 95, 95, 92, so we've got an average of like 94%. So we're quite happy with the model. And I mean, this is quite nice, this one here, that you can see the parasite in here, but this is the beautiful thing about machine learning, because you imagine at the end of a day you've been looking down the microscope trying to catch parasites. You might have just missed this guy, but the AI or the LeNet model didn't miss it. And so we are grateful for our collaborator Abril for giving us the data. And I think what we can say from this video is that Zimmer Peacock, we are a sort of world-leading contract development and contract manufacturer of biosensors. Most of our data is electrochemical in nature, and we're pretty good at AI, and so we can apply those kind of techniques now into the electrochemical domain. So if you have any questions of Zimmer Peacock, don't hesitate to contact us. Okay, thanks very much.